Okay, so before we jump into the heart of 7-3, a quick review of the quadratic formula, because when it shows up something like this, people are always like, I don't remember how to solve that. So I'm going to remind you how to solve this. Do you remember this formula?
Yeah.
I don't expect you to memorize it, so don't worry about that. But if you want to memorize it, have you heard the Pop Goes the Weasel song?
Yep.
Okay, perfect. Sing Pop Goes the Weasel. Maybe you'll have it. So in this setup, there's an A, a B, and a C. What is A from this? Do you remember?
A is the 2 one.
Nope.
The last one.
Nope.
The middle one.
The first one. Oh, I thought you meant this too. You mean x squared. Yes, in front of the x squared. This is A, this is B, this is C, right? So if I'm going to set this up, I'm going to say x equals a negative B is a positive 2, plus or minus, right? Because we get 2 answers. The square root of B, which is a negative, put the parentheses around that, squared, minus 4 times 8 times negative 3 all over 2 times your A value. Is that coming back at all?
Yes.
You're just dropping numbers into a formula, right? Okay, so when you do that, now you simplify. If I were you, I'm not you, but if I were you, I would just take this exactly as you see it and plug it into your calculator. You don't have to. You're welcome to do the mental math all the way through. I just find that one silly little mistake makes a huge difference, and then the whole thing's wrong. So I would probably plug that into my calculator, which would give us 2 plus or minus the square root of, now I'm going to not plug it into my calculator here, but maybe I am. I don't have my calculator. Did anyone plug it in? 4 plus, it's 100. Is it 100?
Yep.
Perfect. Over 16. What's the square root of 100? 10. So this is 2 plus or minus 10 over 16. And now you set it up as 2 separate problems, right? You do 2 plus 10 over 16, and you do 2 minus 10 over 16, and then just simplify that. So this is 12 over 16, which is 3 over 4. And this is negative 8 over 16, which is a negative 1/2. Now, if we're talking about the length of something, which one of these answers is the answer you would use? The positive. You can't have a negative length of something, right? So it shows up in one question. Please don't let it stress you out. If it stresses you out, just move on. I'm not looking to stress you out. It's just a quick little review. You will do a whole lot of this in Algebra 2, okay? But it's just, keep it in your brain for geometry. We're not going to do this one. Just wanted to show it to you. Okay, here we go. 7-3 is proving that triangles are similar. Let's talk back to chapter 4. We did 5 triangle congruence proofs. Do you remember them?
Wait, no, that's...
Alternate interior,
Yeah.
That's different. Chapter 3. What?
SSS.
ASA, SSS, SAS, AAS, and HL, right? We did 5, okay? In this chapter, we're not talking congruence anymore. We're talking similarity. So things are proportional. So there are some different ones in this chapter. Well, really, there's one different one, but there's a whole lot that are not going to be there anymore either. So there are 3, okay? The first one is called AA similarity. And if you recall, on your chapter 4 test, there was a question that said, is there an AAA congruence theorem? There's not, right? The answer was no. But is there an AA similarity theorem? Absolutely, okay? Think about that. In similar triangles, what did we say was true about the angles? They're all congruent, right? So even though the sides won't be the same, the angles will be when they're similar. So AA does exist. So it says if two angles of one triangle are congruent, to two angles of another triangle, then the triangles are similar. Okay, so there is an AA similarity theorem. That's the first one. The second one is there is an SAS similarity theorem. Okay, so SAS with the little tilde, which I definitely do start up now that I've never thought about that before. But it says this: if an angle of one triangle is congruent to an angle of another triangle and the sides that are,
Corresponding.
do you remember the word here? Or the sides that do this?
I thought it was corresponding.
Supplementary.
No.
The one in between.
Complement, no. What does it mean?
It's relational. You always want to be what in a friend group? Included, right? You want to be included. You want to be in the middle. So the sides that include that angle, that put that angle in the middle, those angles are proportional. Then the triangles will be similar. Okay, so if it goes side, included angle, side, where the sides are proportional, but the angles are congruent. Last one. Any guesses? It's one of the ones you already know. Which one do you think works?
ASA. I got it right.
SSS. This is SSS similarity. So it says if the corresponding sides of two triangles, the corresponding sides of two triangles are proportional, then the triangles are similar. Okay? Those are the only three we'll use. So don't try to give me an ASA or an AAS. It will be wrong. SSS is the only, SSS, SAS, and AA. Those are the only three that will work with similarity. Okay? So they'll give you some pictures and they'll say, are these triangles similar? If so, how do you know? Okay. So look at these two triangles. Look at letter A here. Are those similar?
Yes.
Why?
AA.
AA. You have an angle that corresponds to an angle and an angle that corresponds to an angle. So let's write a similarity statement. We would say triangle. So if I say ABC, then you do the tilde, is similar to, because they're not congruent, right? We can see that. Similar to what triangle? YZX. You have to go in the corresponding order. So those are similar by what theorem? AA similarity. Okay, so that's what I want to see from you. Give me the similarity statement and which theorem applies. Okay, this one, letter B. Just looking at this, is AA gonna work? Do we know anything about angles? We don't know any angle. So AA will not work. SAS will not work because we don't know anything about the angle. The only one that has potential here is SSS. What has to be true of the sides if SSS is gonna work? Proportional. Okay, so check that for me. Check if these sets of sides are proportional. Oh, that was a good one, you guys. Sorry. Okay, tell me what you're doing to check if they're proportional.
Find the ratio.
Find the ratio. So like if I'm starting at 14, actually no. Well, yeah. I would say 14 over what? 10. It's got to be the smallest with the smallest, the middle with the middle, the biggest with the biggest, right? So 14 over 10 equals what?
7 over 7.
Oh, sorry, you're reducing. Yes, 14 over 10 equal. I'm going to set up the whole extended proportion. Sorry. So let's go here. 21. 14 over 10 equals 21 over 15, the middle number, right? And then the biggest, 28, over the biggest, the 20, okay? As you see them, those are not the same. but they might be once we do what? Reduce. So divide by 2, you get 7 over 5. Divide by 3, you get 7 over 5. And divide by 4, you get 7 over 5. So are they similar?
Yeah.
Yes. By what? SSS similarity. So we're going to say triangle. Give me a triangle.
ABC.
Nope. I heard 2 different triangles. We'll just go in order on the first one. Okay, so if we say ABC, here's where you have to be a little bit careful.
EFD.
ABC would be, say it again,
EFD.
EFD. Okay, and then you say by SAS, and here's the kicker. Sorry, SSS. That's what I meant. Good job. I was just testing you. By SSS with a scale factor of what? 7 to 5. Not 5 to 7, right? But if you had said EFD to ABC, then you could say 5 to 7, okay? But not on this one, 7 to 5. Questions on that?
So we always have to put the scale factor if it's SS?
If there's a scale factor. Yeah, SSS and SAS should both have scale factors. Anything that has an S in it, because that's the sides being proportional.
S for scale factor.
Okay, this one is not hard, but just requires just an extra little thought to make sure you're paying attention to what we're supposed to be paying attention to. The question is, are the triangles similar? What numbers are we going to use for a triangle ABE?
12, 9,
12 and 9, okay? What lengths are we going to use for triangle ACD?
17 and 12.
Right, make sure you add those together. It's this whole side is 12, right? 9 and 3. This whole side is 17. Okay, so we have 2 sides and 2 sides. That's not enough information. There is no SS. Do you know anything else?
Yes, you know that angle A is similar
Why?
because they're the same. Reflexive. That's
Reflexive. The reflexive property says this angle is the same in both of those triangles, right? So there's potential for SAS, but we have to check, are they truly proportional sides? So I would say 9 over what?
12.
Over 12 is equal to, what's going to go on top over here?
12.
This 12, right? Over what?
17.
The 17. Okay, so take a look at that. 9 over 12 equals 12 over 17. 9 over 12 reduces to
0.
3 to 4. 12 over 17
Does not.
doesn't reduce.
Oh no.
Those are not equal, right? Which means these triangles are not similar. Looked an awful lot like SAS though, right? So just be careful with that. Questions on that? All right. Oh shoot, I never went back and fixed this. This is wrong. I need to make a note of that, or I'm going to do it again next year. Hold on. Geometry notes. Chapter 7. Okay. This should say MP is parallel to what? CA. Yes. MP is parallel to CA, so this first step is MP is parallel to CA. So we're trying to prove that these triangles are similar. Okay, they tell us that this is true. These are parallel, but that's all they tell us. What is step 1 of this proof? Given. Step 1 of every proof that you will do for me. Given. Okay. Step 2 says angle A, and always mark it as you go, right? A is congruent to P, and C is congruent to M. Why do I know that?
Alternate interior.
Alternate interior angles, AIA. Okay, so now we can say the triangles are similar. Why?
Because of
AA similarity. You have two angles that are congruent to two angles. That is AA similarity. Questions on that? Yeah, Nico.
Do you have to prove that both alternate interior angles, or could you do one ulterior angle and then the vertical angle?
You could do one AIA and then the vertical. It would just be an extra step in your proof. But yeah, that's not wrong. Yep, you could totally use those middle ones. Although mine don't look like they actually connect. They're supposed to. There's a funny little dot right in the middle of it. Okay, last thing is indirect. Shoot, I was gonna bring a big mirror today and have you guys go measure some things for me, and I forgot to bring it. Indirect measurement, okay? If you want to know how tall the Empire State Building is, would you find a measuring tape and go stand at the top and drop it all the way down? No, nobody makes a measuring tape that long, right? But because of similarity, because of similar triangles where you could make a smaller version of something and compare them, you could actually very simply measure the Empire State Building if you wanted to, okay? It would require a few things. It would require maybe a measuring tape, maybe a mirror, a few different things to get to that point. Or sometimes you can just use the sun. Today would not be a great day to use the sun because it's not really out, but you can use shadows to measure things. Did you know that? Have you ever done that before? Let me show you in this example what this looks like, and then we'll chat a little more about it. Here's what it says. It says, Ben places a mirror 40 feet from the base of an oak tree. When he stands 5 feet from the mirror, he can see the top of the tree in the reflection. If Ben is 5 feet 8 inches tall, what is the height of the oak tree? So let's draw a little picture, okay? Here's Ben. I am not an artist, so Ben is a stick man for me. You can make him as detailed as you want for you. But it says, so Ben's standing on the ground, okay? That's the ground. And over here is an oak tree. He wants to know how tall that oak tree is. And it says he has a mirror that he puts on the ground. So that when he looks in the mirror, okay, so if I put the mirror on the ground right here, when he looks in the mirror, the reflection sees the top of the oak tree. Why in the world would that information help us measure an oak tree? Yeah, Nico.
Because he knows 40 feet away, and we know that he's 5'8", which means that we can, I don't know how, but we can measure the angle at which he's looking at it to the angle at which it's reflecting. If it hits the exact top of the tree, then you're able to figure out how tall the tree is.
Yeah, why? So what I'm hearing you say is essentially this triangle is similar to this triangle, right? The angles. Which angles are going to be the same right now? Do you know?
So,
Assuming an oak tree grows
the right angle.
up, it's a right angle, right? So he's standing straight up and the tree is standing straight up. So those are right angles. Is there another angle that we know is going to be the same? Maybe you've learned this in your science class. Did you know that the angle you look into a mirror is the angle it comes off of the mirror as well? It's geometry, you guys. It's beautiful geometry. That means this angle has to be the same as that angle. Yes, sir.
Wouldn't it be 5 feet, not 40 feet of the same?
Oh, yes, it is. This is 40 feet, my bad. He is standing 5 feet from the mirror. Okay, so now look at this setup. You have these two triangles. You have 3 lengths. You're looking for a 4th length. What do you do? Yeah.
So you do 40 over 5, and then you get your ratio.
Okay.
And then once you reduce that, which comes out to 9 over 1.
8 over 1.
you put the, you turn the 5 foot 8 inches, sorry, you turn that into inches, so you turn that 5 foot into, sorry, yeah, he's right. Turn it into inches.
Okay, so here's the deal. You don't have to turn it into inches. You could. You could also turn it into feet because that's where we're at already. If you do inches, you're going to get pretty big numbers, and that's fine. You're welcome to do it. But in the end, we probably wouldn't say an oak tree is some 100 inches tall, right? Usually we'd say it's however many feet tall. So on a problem like this, I would probably just use this as a fraction. What's 8 inches as a foot?
3/4? No. 2/3.
2/3, right? 8 inches is 2/3 of a foot, because it's 8 of 12 inches, right? That reduces to 2/3. So I would call this 5 2/3 feet. If you hate that idea, then just turn it all to inches, but in the end, you need to turn it back into feet then, okay? So I would do it this way. I would call this, instead of a mixed number, I would probably go 5 times 3 is 15 plus 2 is 17 thirds feet, okay? Because that's just gonna make our math a little simpler. All right, so this 5/8 is 17 thirds feet. Now you can set up a proportion. So we can say the height of, what was his name, Ben? The height of Ben over what? What does Ben correspond to here?
X.
The X, the height of the oak tree, right? So 17 thirds over X equals, what's going to be your other side?
1/8.
Okay, so if you do reduce your scale factor, 1/8 or 5/40, I don't care which one you do. If you prefer the 1/8, do the 1/8. I'm going to try to keep it just a little more visual right now with the numbers you're seeing. So we'll go this way, but 5/8 is great, or 1/8 is great. So cross multiply that. You get 5x equals 17 thirds times 40. You have options here. If you want to just plug that into a calculator, let me just show you what that would be. 17 divided by 3 times 40 is all you got to do. And you get 226.6666667 on your calculator. What does that mean? You get this. What is that? Exactly. 2/3, right? 0.6 repeating. So it's 226 2/3. The nice thing is they're going to be a little generous here. When you divide by 5, so divide that number by 5, you get this number. X equals 45.3333, right? What is that? 1/3. So this is 45. Oh, I am all over the place here. 45 1/3 is our X value. What does that mean?
Feet.
Feet. The tree is 45 1/3 feet tall. Okay. Now, could you have done it in inches? Absolutely. Convert it all to inches, but then at the end, you would have to do what? Divide by 12 once you find your inches answer, because this would have come out to 544 inches. That's a weird way to measure a tree, I think. Questions on that? Okay.